Hi all. In this session, let's learn about context switching in process management. Interrupts causes the OS to pass the current CPU task and run a kernel routine. When an interrupt occurs, the system saves the current process context to resume later. The context is stored in the process control block, that is PCB. The context includes CPU register, process states, and memory management information. The OS performs a state saved before handling the interrupt and state restored to resume the process. Context switching is a process where the operating system saves the state, that is, context of the current running process, and loads the saved state of another process, allowing the CPU to switch execution from one process to another process. Now let's discuss the need for context switching. The first comes multitasking illusion. It allows multiple processes to share a single CPU, making it look like they are running at the same time. The next is CPU utilization. It keeps the CPU busy when a process is waiting for I/O by switching to another ready process. The next is fairness, which ensures all the process get CPU time and no one hogs it forever. The responsiveness is essential for interactive system so that the system can react quickly to the user input or urgent task. Priority handling allows the operating system to switch to higher priority or real-time processes when needed. Fault or interrupt handling enables the operating system to handle events like hardware interrupt, traps, or system calls immediately. These are the reasons why context switching is important in operating systems. Now let's check out the steps involved in context switching. The process involved are P0 and P1. P0 is available at left side of the operating system and P1 is available at right side of the operating system. Only one process is executed at a time, that is P0 is executing. The other is ideal. P1 is ideal here. A trigger, that is an interrupt or a system call, forces the CPU to stop the current process. Now, context switching is performed. The steps involved are: first, we have to save the current process state into the PCB. That is, the process P0's PCB is saved to PCB 0. Next, we have to reload the next process states from its PCB. The process P1's PCB is PCB1. Now, CPU runs the new process P1, whereas P0 is now ideal. The cycle repeats again. That is, later another interrupt or system call causes the OS to save the P1 state into PCB1 and reloads the state of PCB0 and resumes P0. Now, process P1 is ideal and process P0 is executing. The key idea is the operating system is in the middle and managing these save and load actions. During this time, no real work from the processors is done. It is pure overhead. Now we can learn about the drawbacks of context switching. Switching CPU from one process to another process is purely a context switch overload. It involves saving the current process states in its PCB and restoring the new process state. The time spent in saving the current process state in its PCB and restoring the new process states is purely overhead. It takes time but does no useful computation. The factors that affecting the context switch performance depends on memory speed, number of registers, special CPU instructions for quicker save load of process state. Frequent context switches can degrade overall system performance. Too many switches can increase response time for processors. Managing context switch adds complexity to OS design. Some CPU have multiple register sets in order to perform faster switch, that is, just change the pointer from one set to another set. If active processors exceed register sets, must copy the register data to or from memory which is lower.
Thank you all.